Sure. So, hi, welcome to the next DSI seminar. My name's Jaz Seacon. Today, we're very happy to have Thomas Richardson from the Department of Statistics from the University of Washington, where he also directs the Center for Statistics and the Social Sciences. He has an affiliation with the Economics Department. He has a PhD in statistics from CMU and undergrad from Oxford. More importantly, for our purposes, he's one of the world's leading experts on causality in graphical models. And today, he'll be talking about that with joint work with Jamie Robbins from Harvard. Some of you may know that Jamie presented an early version of this work last year. Thomas has slides, so by definition, there'll be no slides in common between the two talks. Without further ado, here's Thomas Richardson. Just two quick announcements. First is I know a lot of people some people often have to leave around 2 for a class. If you could like leave around 1:55, like sort of together and as quietly as possible, that'd be great. And second, we are videotaping this, so if anyone has any questions at any time, please raise your arm and someone will bring a mic to you so the question is clear on the videotape. Thanks.
That better? So my PhD was from CMU, but it was officially in logic, computation, and methodology, and it was from the philosophy department. So my colleagues always say I have a real PhD, is the way that they describe it. So I'm going to give here's a quick outline. I'm going to give a review of counterfactuals and graphs, two different theories, approaches to formulating causal models. And then I'm going to talk about a unification of graphs and counterfactuals via node splitting. And as Jaz said, Jamie Robbins presented some of this work a year ago, but by his own assessment, he very much enjoyed giving a talk and the feedback that he received from the audience. But he also was of the opinion that there might be a few loose ends, and there might be some possibility for it might be worthwhile giving a follow-up talk. So I'll present this unification. I'll give some very simple examples. I'll then give you a general procedure and talk about two properties that I call factorization and modularity. And then I'll contrast the approach that I'm presenting here with another approach due to Judea-Pearl called the twin network approach. And I'll do that in context of example. And then I'll show some further applications of the theory in terms of adjusting for confounding, sequentially randomized experiments or time-dependent confounding. I'll very briefly show you just a glimpse of how it extends to think about dynamic treatment regimes, and then I'll have some concluding remarks. So starting here with David Hume, who comes from my hometown of Edinburgh. And he was an 18th century philosopher. You've probably all heard of him. And he states the following. He says, "We may define a cause to be an object followed by another, and where all the objects similar to the first are followed by objects similar to the second," which sort of in 18th century parlance is saying that if there's a causal relationship, we would expect there to be some kind of association. And then he goes on and he adds this qualification where he says, "Where if the first object had not been, the second never had existed." Okay, so he's switched into using a subjunctive mood here. He's not talking about what actually happened, but what would have been observed had things been different. And I also should mention here that although he made this comment, philosophers, I presented this to sort of philosophers of science, and they were very unhappy because Hume is famous for 3 causal theories, but this wasn't one of them. And apparently this was just a brief aside that has not gone anywhere in philosophy, but it has gone quite far in statistics. So by way of truth in advertising, I want to let you know that. So we then jump forwards to Neyman. And this is from Neyman's master's thesis in Polish. And he says that if we have, he's thinking about field trials where we have a field divided up into various plots, and we're planting different species of grain, or it could be that we're trying out different fertilizers. And he says to compare V varieties on M plots, we will consider a set of numbers, a matrix of numbers like this, where Uij is the crop yield that would be observed if variety I were planted in plot J. Okay? And the key point is that the experimental constraints mean that we can only plant one variety in a given plot, and so consequently we are only getting to see one number in each column. Okay? But we're going to conceptualize that the set of numbers exists. Even though we don't get to see all of them, we're going to suppose that these are the results that we would observe under all of the possible experiments that we might have carried out. So we only get to see one number per column. So now I'm going to simplify things even further. I'm just going to, a lot of the next few slides, I'm going to think about a case where we have a binary treatment X and a response Y, which we'll also suppose is binary. And so this then leads us to think of two potential outcome variables, y of x equals 0 being, for a given subject, the value of y that would be observed for that unit if assigned to x equals 0. Okay? So each subject is going to have one variable telling us what would happen to them if they got x equals 0 or placebo, and they're going to have another variable, y of x equals 1, which is the value that would be observed for that unit if assigned to x equals 1. Okay? And these are just two different random variables. So the parentheses here are not indicating a realization. They're just indicating two different random variables that that happen to have these two different names. And I'll also often, to keep things short, I'll often write them in this way to keep the notation compact. And it's implicit here, whenever we're writing down one of these potential outcomes, it's implicit that they're well defined. And so in particular, we're sort of implicitly assuming here that there's only one version of treatment, so that if I say x equals 0, if I say placebo, then that's well defined, that there is a specific outcome that's well defined for you under placebo, and there's a specific outcome that's defined for you under treatment. And we don't have to worry that, well, there might be perhaps different versions of treatment. And we're also going to suppose that there's no interference between units, so that Jazz's outcome, if he were to receive the drug, doesn't depend on whether or not I also received the drug, which in certain settings is reasonable, but if you, in the context of something like a vaccine trial for an infectious disease, might not be reasonable. I also should note I'm going to use the terms potential outcome and counterfactual synonymously in this talk. Sometimes people distinguish between these. There are certain distinctions people make, but I'm not making any distinction there. Okay, so just to take these ideas a little further forwards, in the simplest case, with a binary outcome, we can now think about 4 different types of patient. We can think about patient, say here, who has a bad outcome, regardless of whether they were to receive the drug or the placebo. They both are 0. A patient who's of type helped, who has a good outcome, would have a good outcome if they received the drug, but would have a bad outcome were they to receive the placebo, and similarly hurt and always recover. And given these potential outcomes, so if we knew what they were, then the observed data under any particular experiment can then be generated from these potential outcomes in the following way. So here I'm considering a simple setup with 5 different patients like this. The first patient is assigned to treatment, second to control, and so on. And then now when we want to look at what are the outcomes that we observe from our experiment, they're constructed in sort of the obvious way that you would imagine. So the first patient was assigned to x equals 1, so therefore their observed outcome is this guy y of x equals 1. The outcome for that patient were they to be assigned to x equals 1. And likewise for each one of these patients. We don't get to see the outcomes although we can conceptualize them as existing, we don't get to see the outcomes for the treatments that are not assigned. And so in each row of the table here, we're going to see there's going to be one entry that's known and one entry that's unknown. So in fact, this person was in fact of type helped, but all that we know is that they received the drug and had a good outcome. So from our perspective, they could be of type helped or type always recover. So a quantity of interest, I mean, there are many quantities that might be of interest, but one particular quantity of interest is the average causal effect of x on y, which is just the difference between the expectations of these two potential outcomes, which also corresponds in this simple setting to the difference between the proportion helped and the proportion hurt. And we can also think about this as the difference in percent in the proportion of people recovering if everyone were treated versus if no one were treated. Because if everyone's treated, then the people that will have a good outcome are those of type always recover and helped. If no one is treated, then those with a good outcome will be of type always recover or hurt. So subtracting one from the other, we get helped minus hurt. Okay, so if x is assigned randomly, then if treatment is assigned randomly, then the x will be independent of our potential outcomes. And then basically we can then get from here, this is our definition of the average causal effect, just by laws of expectation. This is the difference of the averages. And then using these independencies that we have up here, we can then condition on x equals 1 here and condition on x equals 0 here. And then remembering how our observed data is related back to these potential outcomes, this then simply becomes the expectation of y given x equals 1 and the expectation of y given x equals 0, which are observed. Okay, so this is probably familiar to many of you, under randomization, then our average causal effect now becomes identified from the observed data. So just to contrast that, and also to help you sort of take in some of these concepts, we could contrast that with a situation where there is no randomization. So suppose that treatment is not randomized, and I give you this data set. So I say, here we had 2,000 patients. Here are their outcomes. We have, it turns out that 1,000 got the placebo, 1,000 got the drug, but they weren't necessarily randomly assigned. What can we infer about the average causal effect of x on y in this circumstance? Well, so now I'm asking you to think like a lawyer now. Think like a lawyer, not like a statistician. So let's suppose we're a lawyer for the drug company. So what's the largest number of people who could be helped? Okay, well, these guys down here, they got the placebo and they had a good outcome. So we're going to have a hard time arguing that those are of type helped, because we didn't give them the drug and they still had a good outcome. Likewise, these people up here got the drug and they died. Again, even for a lawyer, it's going to be hard to claim that those people are of type helped. But these people here got the placebo and they died, so we're going to claim that all of them are of type helped. If only they'd been given the drug, they'd still be alive today. And of course, all the people down here who were given the drug and lived, we're also going to argue that, of course, they're all still alive because they were helped. None of them are of type always recover. So we're going to basically claim that we've got 600 people out of 2,000 who are of type helped. And likewise, we're trying to argue the strongest case possible for the drug company. So what's the smallest number of people who could be hurt? Well, if we think about it, as a lawyer, do we have to admit that anyone was hurt? We don't. Yes. Sure enough, there were these 600 people that got the drug and died, but obviously those were people that were just, hopeless cases. They were going to die no matter what we did. They must have been of type never recover. And likewise, the 800 people down here who lived even though they didn't get the drug, they must have been, indestructible. And so we're going to claim that all these people down here are of type always recover, all of these people up here are of type never recover. So we're going to claim that no one is of type hurt. Okay? And so our estimate of the average causal effect is going to be 0.3. Okay? So this is looking at the data and trying to work out what scenario is compatible with the largest value of the average causal effect. Similar logic, now attacking the drug company. If we're trying to find the minimum value of the average causal effect, we're just going to turn it around and we're going to claim that there's absolutely nobody who is of type helped. Yes, sure enough, these people we're going to claim were of type always recover, these people we're going to claim were of type never recover, and we're going to claim that these people are all of type hurt. So we'll end up with our minimum value will be negative. Those of you that sort of have looked at two-way tables will realize this is just, I'm just presenting the Frechet bounds here, but the key point is that, that they're going to straddle zero. So we have learned something. In the absence of randomization, there is some good news. We have learned something. The range of the average causal effect previously was from -1 to 1. We've narrowed it down to -0.7 to 3. That's the good news. The bad news is that we've still got 0 in the interval that we have, and so we can't. We don't know whether the drug is harmful or helpful. Okay, so and this is the general scenario. It's sort of easy to see from the same kind of logic that the bounds on the average causal effect are always going to cross 0. So the key point here is that, that without randomization, we're going to get much weaker inferences. In fact, we're not going to be able to infer that in this simple two-variable case, we're not going to be able to infer that something is effective or harmful. So just to summarize what I've been through, we've seen that for each unit, one outcome is actual, the others are counterfactual. And the key idea here is that you sort of see we started out with this notion of causation, and through this mechanism of potential outcomes, we've reduced it to missing data, okay? Which I sometimes describe this as causation is something that almost everybody gets excited about. Missing data is something that statisticians get excited about, but not quite so many other people are excited by missing data. And so but the sort of good news is that this is conceptual progress. And we saw that the average causal effects identified if we have these two marginal independencies holding, and those would be implied by randomization of treatment. And this is, I'm just giving you the absolute sort of tip of the iceberg here. I'm assuming that most of you have come across this model at some point previously. These ideas are central to Fisher's exact test, many parts of experimental design. And a key point here is that, that there are many applied causal data analyses published in Biostatistics, Econometrics, and Epidemiology that are based on this particular theory. So sometimes, you may sometimes have heard people sort of try to suggest that, that sort of statistics has shied away from formulating causal models. This is not the case. There are many causal models formulated in statistics, but most of them are done within the context of this. I mean, it has started to change recently, but until relatively recently, a lot of them have been done within this particular framework, and particularly in biostatistics and econometrics, this framework is really predominant. Okay, in case there are people that have thought about things have come across the graphical framework that I'm about to talk about in a moment, and have sort of come across this do notation that was introduced by Pearl, I want to just take 1 second to relate what we saw in terms of potential outcomes to the do notation. So this quantity here, it would be written in the do notation in this way. So this is just an alternative notation for the distribution over y if we were to assign everyone to x equals x that was introduced by Pearl. It should be said that the counterfactual notation is more general because, for instance, in the counterfactual notation we could do something like, we could ask, among the people that received treatment, we could think about the distribution of outcomes that would be present in that subgroup if they had received placebo. Okay? So we could talk about, in the context of this missing data framework that we saw, we could formulate this. This is sort of those of you who have seen this before, this is 1/2 of the effect of treatment on the treated. So we know what, we observe the distribution of y of x equals 1, conditional on x equals 1. Those are just the observed outcomes, but this quantity will not be directly observed, although we can make assumptions and make inference on it. So yes, if in the context I saw before, I considered before where treatment was randomized, then this quantity is obviously just equal to the distribution of outcomes if everyone were assigned to placebo. But in an observational study where people are maybe selecting treatment because they know something about how they may respond to it, these two quantities need not be the same. Okay, so the summary point here is not that it's so crucial to understand this quantity. I just want to make the point that anything that's written in the do notation can be rewritten in the counterfactual notation, but the counterfactual notation is more general. There are certain quantities that exist in the counterfactual notation that can't be directly transformed into the do notation because, for example, here, x is both taking the value 0 here and we're conditioning on x being 1 here. Okay, so now I'm going to briefly talk about graphs. So set causal notions just to one side for a couple of slides, even though I'm going to show you graphs and they look very suggestive causally. For the moment, let's just think about them purely as describing properties of a distribution. Okay, so I'm going to associate with a directed acyclic graph, and directed acyclic graph just means we have a set of nodes that correspond to random variables, and we have directed edges between them, and we're not allowed to have a directed cycle. So if we're following the edges, we can't start at a node and get back to where we began. And we associate with this graph a factorization of a joint distribution over the random variables corresponding to the vertices, and that factorization just factorizes into a product of densities for each variable conditional on its parents. So, for instance, if this is our graph, then we would associate with this graph a factorization into P of A, because A has no parents, P of B given A, C given A, D given B and C, and then E given D. And so I should say I'm using a graphical terminology here that if there's a directed edge from A, for example here from A to C, then A will be said to be a parent of C and C is a child of A. So I don't have time to lay out the full definition here, but there's a relatively simple graphical rule that means that I can stare at the graph, and if somebody comes along and asks me the question, if I were to give you a joint distribution which factorizes according to that graph, and for 3 sets of variables, say x, y, and z, is it the case that x will be conditionally independent of y given z? Then this graphical rule allows me to look at the graph and read off directly from that graph whether or not it is the case that for every distribution factorizing according to graph, x is independent of y given z. That rule is known as d-separation. And some level, for the purpose of this talk, all you need to know is that we look for the absence of a certain kind of path between x and y conditional on z. If there's no path of a certain form between x and y conditional on z, then it will hold that any distribution factorizing according to graph x will be independent of y given z. And there's furthermore a completeness property that says that if there is a path of a certain type, then there will exist a distribution that factorizes according to the graph where that independence does not hold. So here are sort of 2 instances of this. So one is that, so here, any distribution which factorizes in this way, it will be the case that E will be independent of A, B, and C, conditional on D. It will also be the case that D is independent of A, conditional on B and C. So all of those sort of you could, just by guessing how separation works, you might be able to sort of heuristically guess those if you came across these on a multiple choice exam. But here, this is one more, that C is independent of B conditional on A, but C is not independent of B conditional on A and D. Okay, enough of that. So up to this point, all I've had is a graph and a factorization of a joint distribution. There's nothing, I've not said anything causal whatsoever up to this point. Right? In fact, it's the case that if a joint distribution over x and y factorizes according to the graph where x points to y, then that's a trivial factorization, and it will also factorize according to the graph where y points to x. So now the question is, in order to build in, to link this up to causal notions, I need to add in some more structure. I need to add in some more assumptions. And the basic idea is that there's a convention when people write down a causal graph. When they want to interpret it causally, there's a convention that says that if there is an unobserved, if there's a variable which might be unobserved, that's a confounder between x and y, then it must be included on the graph. So in particular, the convention is that if I write down this graph, then I am asserting that there is no confounding variable between x and y. Because in order to interpret the graph causally, whenever there is such a confounding variable, I'm obligated to include it on the graph. I should say the graph is intended to represent direct causal relations. I've said that already. And this approach goes back to, just as the counterfactual approach goes back to Neyman's work in the 1920s, this approach goes back to path diagrams, which were introduced by Wright also in the 1920s. And yes, I said this already. X points to y, x is a parent of y, y is a child of x. Okay, so here's the idea. If I write down this graph, I'm supposing that there's no confounder between x and y. Here is the factor. This is the simplest graph imaginable, or the simplest graph containing an edge. Here is the associated factorization that I have. And in the absence of confounding, the causal model now asserts that the distribution over y, when I intervene to set x to x, which can also be written like this in this alternative notation, will be equal to the distribution of y conditional on x. Right? That is the way that the causal interpretation of a graph is set up. Okay? So if I write down this graph, then I am asserting that if you're interested in this distribution here, I can obtain it from the conditional distribution of y given x. Okay? Sometimes this is referred to as an operation on a factorization, so sort of you cross out this term from the factorization. Sometimes called the truncated factorization formula. Okay, so that's the graphical approach to causal modeling. And the question is, how does this relate to the counterfactual approach? And so I preface what I'm about to present by saying the way that I'm going to show of relating these two approaches is very, very simple. But I think that it is necessary because currently we have people working in biostatistics, sort of people very open to, people formulating causal models, very open to causal analyses and ways of thinking in biostatistics and econometrics who are using potential outcomes. And then there are other people in computer science and epidemiology and a number of other fields who are formulating models using graphs. And when they try to communicate, the epidemiologist will write down a graph, and then the biostatistician will say, that's great, what does that graph mean in terms of potential outcomes? And often there's then a gap, basically. It's not, the person using graph is not able to easily describe what the model represents in terms of assumptions about counterfactual random variables. And so I've taught classes, for example, with people who start off describing the potential outcome approach, and then I describe the graphical approach, and then people ask, well, how do these two things relate? And the answer is that it's prior to the approach I'm showing you, it has not been very easy to relate these two approaches. And so, yes. So I make no apology for the fact that the approach I'm going to show you is very, very easy, but it's designed to be easy in order to facilitate communication between these two different camps. So here I'm laying them next to one another. This is the graph. As I said, if you don't include the unobserved variable, this represents that we have no confounding between x and y. In the counterfactual approach, we would represent similar assumption in this way by having these two marginal independencies. In the other way, if we have the graphical approach, if we have confounding, then we have this hidden variable. And at least one of these independencies fails to hold. So you might think, right, I told you, I motivated the graphical approach by saying, these are graphs, they're really good, we can use them as this way of reading off conditional independence. I give you the graph, come to me with an independence query, then I can give you this rule, you can sit there and stare at the graph and read off independence, using Pearl's d-separation. I want I should have said that earlier, I want to be clear about that this d-separation rule was due to Judea-Pearl. Okay? So everything I'm going to present that uses d-separation is building on Pearl's earlier work that came up with this particular rule and also proved that not only was it sound, but also it was complete in the way that I described. So, right, I give you this graph, I tell you it has a causal interpretation, I tell you we can read off conditional independence properties from this. You might think to yourself, well, okay, right, so we understand that no confounding means these two independences hold. Surely I should be able to read that off the graph, right? These are independences, we've got a graph, it's causal. But there's obviously an elephant in the room here, which is that I don't actually have these two variables on the graph, right? It doesn't matter how long I stare at them, those variables do not show up on the graph, so I can't read those independences directly off the graph, right? And so I'm going to present a very simple approach. We're going to transform the original graph into a graph that now contains some counterfactual variables, and then in that graph, using Judea-Pearl's d-separation, we are going to be able to read off counterfactual independences. Okay? So here's the picture. I start off with the graph like this, representing the original distribution. I then slice the x node into two pieces. The first piece here is random. The second piece here is going to be the fixed part. And then everything downstream of this fixed part will now become a counterfactual variable labeled by the fixed value that x has been fixed to. And these random nodes, although this is a semicircle, that's just to remind us where it came from. I want you to think about the random nodes, even if they're semicircles, as just like nodes in an ordinary graph, no different from any other node in it that you might see in a graph. Okay, and now, even if you don't know d-separation, I told you that d-separation says in the absence of any path between two nodes, we get independence, where you can see here I've got x, here I've got this node over here. There are no paths between these two, right? Because this is just a separate node sitting here, and there's no pathway from here to here. So even if you sort of don't know the full definition of d-separation, you can sort of see that this independence should be coming off this graph. I'm also going to associate a new factorization. So here I'm going to use this graph to represent, just as this graph represents a joint distribution over x and y, this new graph is going to represent a joint distribution over x and y of x equals 0, the two random nodes that we've got. Okay? So here is the joint distribution that I'm representing, and I'm going to, just in exactly the same way as before, require that the joint distribution over the variables in the new graph factorize according to the graph. Okay? So here, x has no parents, so this is the term that we get here. And then y of x equals 0 also has no random parents, so again, we just get the trivial factorization into these two pieces, both just simply being marginally independent. Okay? So that's the factorization. The factorization is exactly the same as the earlier DAG factorization, modulo that we're just ignoring the fixed nodes. And that's basically it. Other than that, it's identical to the earlier factorization that we saw. There's one more thing, which is I need to tell you what this distribution is here. Okay? So I've got this, so far I've started off with this graph, I've done this transformation, I'm now telling you that the new graph represents a factorization over the random variables in this new graph, and that it factors in the same way as before into each variable conditional on its random parents. But I need to tell you where you're supposed to obtain this distribution from. And that's done in the sort of the thing which might seem natural and intuitive, which is that I'm going to obtain this piece by going up to the density that was associated with y before I did the transformation and just plugging in the value x equals 0. Okay, so I'm going to plug in, if you ask me what's this marginal density over this variable here, y of x equals 0, I'm going to get that from the original observed distribution of y conditional on x equals 0. So this second assumption is what I refer to as modularity. It tells me how to get the terms in the factorization, how they relate back to the factorization of the original observed distribution. Okay, so this was with x equals 0. We can do exactly the same thing with x equals 1. Okay, here I've fixed this to x equals 1, and I'm labeling everything downstream from there. I now get a factorization, but now it's over two different random. This random variable is the same, but now this is y of x equals 1. Again, I get y of x equals 1 has no random parents, so again we get the same trivial factorization, and then, not terribly surprisingly, I then get this marginal distribution over y of x equals 1 from my original distribution, but now instead of plugging in x equals 0, I'm plugging in x equals 1. Okay? So you might wonder, why do I belabor this point? Why do I plug in x equals 0 and x equals 1 separately? And there's a sort of key idea here, which is that so I'm calling the new graph that I'm constructing here a Swig, for reasons that will become clear in a moment. This is Jamie's name. I'll tell you what it stands for in a second. But basically, g of x0 represents the joint over these two random variables. This is a typo. This should be g of x1 represents the joint over x and y of x1. And under no confounding, these marginals are identified from the original joint distribution. So each of these graphs, this one and this one, represent joint distributions over counterfactual variables that are identified under the assumption of no confounding. In contrast, if I'd been more ambitious and I'd tried to build a graph which had all three of these things on, x, y of x0, and y of x1, then I would now be talking about a marginal distribution that's not identified, for the reason that we never get to see for any individual both their outcome under y of x0 and their outcome under y of x1. Okay, so there's no information. In general, the joint distribution for the margin over y of x0 and y of x1 is not identified. Okay, so I'm never constructing a graph that has both of these on the same graph. Okay? So within this framework, although I'm going to have these two independence assumptions, I'm not necessarily assuming this. Okay? So in the ignorability terminology, I'm assuming weak ignorability and not strong ignorability. And you might say, well, isn't this a bit pedantic? I mean, if I randomized x, why wouldn't I believe this? And the point is that in the context where it's just two variables and x was randomized, there's nothing wrong with this assumption. But in the context where there are more variables, then it starts to become problematic. You can easily start introducing assumptions about joint distributions that are not identified from any feasible experiment. And those assumptions can even lead to additional identification results. I won't have time to go into all of that in this talk, but I have extra slides if people want to ask me about that at the end, where I can explain what the issue is. Okay, so the key point is that so SWIG stands for single world intervention graph, because we're not going to have both of these. It's a single possible world, basically. We're not going to have both of these random variables on the same graph. Okay. You might say, well, do I really need to make a new version of this graph for every value of x? Supposing I've got countably many of them, supposing I've got infinitely many of them, isn't it going to take me rather a long time to write out all these graphs? Of course, I can represent all of them just by a template like this, right? We can all see, okay, I can think of this as representing both the graph with x equals 0 and the graph of x equals 1, but it's important to be precise about what we're doing when we're doing that this thing over here then is not a graph in the usual graphical modeling sense. This is now a graph-valued function, not a graph. So the idea is you come to me with your favorite value of x, say x equals 0. I then plug it in, and I give you back a graph, and then you're then representing the joint over x and y of x equals 0. Or if x equals 1, we get the other graph. Okay? Those of you that have sort of used bugs and sort of know about plates, there's sort of similar ideas that are present in the bugs framework with plates. But so you should think about this as, when I'm using a template like this to represent several different SWIGs, you should think about this as a function that takes in a specific value and then gives you back a graph. Okay? So if I stick in x equals 0, I get this SWIG, stick in x equals 1, I get this SWIG. Okay? And each SWIG represents a different margin. Okay? So it's not that this graph is representing the joint over x, y of x0, and y of x1. Okay, so let me take a little pause here and give you a bit of intuition behind this node splitting. So you might ask yourself the question, okay, so I've got this graph, I've got x, and I've got y of x equals 0. So how could we possibly find out? How could we find out who are the people that would choose to take treatment, say, in an observational study, and at the same time find out what would happen to those people under placebo? Right? So supposing that Jazz is very keen on this drug, and he's going to, in an observational setting, he's going to grab it at the first available opportunity, but we want to know, because we want to evaluate the effect of treatment on the treated, we want to know what would happen to Jazz if he didn't take the drug. So as some of you may know, Jamie Robbins is an MD, and so he came up with this sort of thought experiment where basically what we do is we carefully monitor we get the NSA data feed and carefully monitor the behavior of the patient, and then just at the moment where the patient's observed to swallow the drug, so that we know, yep, they've swallowed the drug, they would definitely be one of the people taking the drug. Jazz just swallowed it. We've seen that from his webcam. And then we instantly intervene and administer a safe emetic that causes the pill to be regurgitated before any drug can enter the bloodstream. And then we see what his outcome is. Okay? So in this way, we both know that Jazz is in the group that would take treatment in the observational study, and we get to see what would happen to him under y of x equals 0. And we're assuming that this emetic has no side effects. So it's not that anyone would actually propose doing this experiment, but conceptually, this is the thought experiment corresponding to what we're doing in the graph where we do this slicing. Okay? You can think about this as the cut here is the cut that's going on when we are observing the value of x and then intervening and then finding out what happens downstream of y of x equals 0. So this is a slightly violent scenario. But I mean, there are less violent scenarios where this actually happens, say where people will sign up for, say, housing vouchers or extra tutoring, but then there aren't enough housing vouchers or tutoring available for everybody that would like to participate, and so people are subsequently then randomized, and not all of them get to take the treatment. And so that would be a less violent setting where maybe you get to see who are the people that would like to take the treatment, and you get to see what happens if they don't get it. Okay, so now that was the sort of thought experiment set behind this slicing. So now let me just show you some applications of this theory. So supposing that I give you this graph, and I ask you, so this is the kind of thing which happens when you have an epidemiologist and a biostatistician sort of talking to one another. The epidemiologist might write down a graph like this. In this particular setting, A and B are both treatments, and then the biostatistician says, okay, that's great. Does that graph imply this? Does that imply this independence, counterfactual independence? Say, because if it does, then I can apply. I know something's identified. Here's how we can solve it. We just apply this slicing technique. So now I've upped the ante a little bit. We're now cutting on two variables. So we split on A and we split on B in this way. And then now we can read off from the graph that yes, y of AB is d-separated from B of A, conditional on Z of A and A. So we can just read that off using d-separation. We can see that this conditional independence holds. Okay, and so I'll come back to this example a little bit later. So that was an example where we are now making two interventions. So now, after having shown you that, let me now give you the general the general scheme. So in general, if you come along to me with a graph and you say, I want to intervene on a set of variables, subset of variables, we split all of those variables. And to say that formally, when we do the split, there'll be a random half and a fixed half. The random half will get all the parents, all of the edges directed in, and the fixed part will get all the edges directed out. And then we then let we then do our relabeling, and the relabeling just percolates downwards. Okay, so here we've got this fixed node A, and everything downstream from A is then going to get labeled with A. But it's important we do all of the splitting first, and then we relabel downstream. So for example, B has also been split here. So if B had any children here, they don't get labeled with A because we've done our split. Okay? So that's the procedure. 2 steps. First step, split the variables that for which we're interested in those counterfactuals. The second step is to allow the fixed nodes to sort of percolate downwards and label everything that's downstream from them. Okay, and then that gives us the template, and then in order to obtain a SWIG, you then put in your favorite values for A. And then a little bit of notation. I'm going to use this black or bold V of x to represent, to be the set of variables that the SWIG contains. So the SWIG G of x tilde represents a joint distribution over these counterfactual random variables. Okay, so there are 2 assumptions, as I said. This is just generalizing what we saw before. The factorization just says that the joint distribution over the counterfactual variables in the graph after we've done our transformation factorizes in exactly the same way that we associate factorizations with graphs. Previously, just ignoring the fixed nodes. The second assumption says that the new joint distribution is linked to the old distribution by just saying that the conditional density associated with y of a tilde y, this is the new vertex in the new graph, is just the conditional density we had in the original graph, substituting ai for any variable that we've split. And the consequence here, you can sort of see, is that if we observed all the variables in the original graph, then the joint distribution over the counterfactuals in the new graph is identified. Okay? So that all of the graphs we're constructing this procedure, the joint distributions will be identified if all the variables in the original graph if the joint distribution in the original graph was also identified. So the other thing we want to do is we want to have a deseparation criterion. So we want to have a way to read off conditional independence from the graph. And basically, we just apply deseparation in exactly the same way, except that we have to remember to also implicitly condition on the fixed nodes. Right? And another way to do this is we could simply remove the fixed nodes from the graph. Okay? So if you ask me, is B independent of C given D in the SWIG, in a joint distribution represented by the SWIG, I check whether B is deseparated from C given D and the fixed nodes. Okay? Which makes sense because we're thinking of the fixed nodes as fixed. Okay, so here's a little example. This is a sort of mediation graph, have zx and y, no confounders. Now, this is the original factorization we have. It's just a trivial factorization of zx and y. If I now intervene on z and x, I get this graph over here. And now you'll see that nobody has any random parents. So x of z doesn't have any random parents. Y of xz doesn't have any random parents. Here's my factorization, trivial factorization. Everything, all of these variables are independent. Modularity now tells me how these pieces are obtained from the original graph, just in the way that we generalized previously. And deseparation gives us that all of these variables are marginally independent. If I didn't have the edge from z to y, then instead of having y of xz here, now there's no pathway from this fixed node to y, so therefore this just gets labeled with y of x. And now our graph represents this joint distribution, which factors in this way, and we get our marginals back from the original distribution in exactly the same way. So deseparation, again, now gives us that the variables that show up on this graph, z, x of z, and y of x, these are all jointly independent. Okay, let me just briefly come back to this problem and say why I presented this. So Pearl has an example. I've relabeled two of the variables, but Pearl has an example basically identical to this in his book, where he argues, he looks at this graph and he says, using his approach to unifying graphs and counterfactuals, that this graph doesn't imply this particular independence. So he claims that there exists a distribution, there exists a counterfactual model compatible with this graph where this independence doesn't hold. But in fact, we can see, we read off the Swig earlier that this variable is independent of this, conditional on this and this. So we got this independence just by applying deseparation to this Swig. And then we can then, if this holds, then we could also condition on a being equal to little a. And then we can go from here back to here just by consistency. Because if we're conditioning on a being equal to little a, then z of a is just z, and b of a is just b. That's just the way that I showed in the beginning, that the observed data is linked to the counterfactual data. And this is slightly interesting because I believe that Jamie may have mentioned this in his previous talk, but there's a joint paper between Judea Pearl and Jamie Robbins that has a number of results in it, and Judea thought that this result in his joint paper with Jamie was incorrect based on this particular example, but in fact this independence does hold in this graph, and so it turns out that collectively they hadn't made any mistake in their original paper. But more interestingly is sort of why Pearl made this incorrect conclusion. And in order to do that, I'm just going to briefly show you the way that Pearl would have addressed this question. Okay, so here we've got this graph here. In order to look at these counterfactual independencies, we constructed the Swig in this way. Pearl has a different way of doing it, whereby he calls this the twin network approach. So he starts off with this graph like this, and he then makes two copies of it, one here and a second one over here where he's done the intervention. And he then joins the random things together. So everything over here gets labeled with AB, which is different from the way that we've been doing things because he's not doing the percolating downwards. But he links together everything via error terms, and significantly independent error terms. And he then looks at this graph and he says, he would then check, well, is there a deconnecting path between y of AB here and b conditional on z and a? And there is. Right? There's this path that goes like this. We haven't conditioned on any of the variables in this path. And if you read carefully his discussion, it's clear that because of this path, he thinks, well, there's a deconnecting path, so therefore, presumably, this independence doesn't hold. But the problem in his reasoning is that there are deterministic relationships that hold amongst the variables in this graph that are not being represented, not being explicitly represented. So in particular, if your naturally occurring a value is equal to little a, then your naturally occurring z value is equal to z of little a, which is also equal to z of AB here because there's no pathway from B to Z. Okay, so consequently, when we're testing this deseparation relation, although we're conditioning on Z and A, if we condition on Z and A equals little a, we're also actually conditioning on this guy over here, because if A is equal to little a and we know the value of Z, then we also know the value of ZAB. And so consequently, this pathway is blocked. And basically, so another way of saying this is that, you remember I said if I have the graph and I find a deconnecting path, then there's some distribution which factors according to the graph in which the corresponding independence does not hold. This was a result, this is the completeness of deseparation, one of Judea's sort of most important results relating to deseparation. This breaks down here because of these deterministic relations between A, Z, and Z of AB. So basically, if I know A and I know Z, then I know this variable over here. That's not explicitly represented in the graph, and that's why Pearl's inference from the presence of this path to concluding the independence didn't hold is not correct. Okay? Ilya Spitzer and Judea Pearl sort of realized that their procedure had this bug, and they introduced a pre-processing step to try to address this. A pre-processing step involves doing pre-processing on this graph to marry nodes together in order to then check these counterfactual dependencies. But the pre-processing step is not very easy to apply, and a sort of testament to that is the fact that, in this last chapter of his book, he doesn't apply this. Had he applied that pre-processing step, he wouldn't have made this error, but he didn't do that. So the bottom line, and the key message here is that there was a unification of graphs and counterfactuals that's been presented before, but sort of as you can see, even without going into too many details, you can see the graph we've got here is more complicated than the graph that we had here. I'm not saying this is the simplest graph ever, but it has fewer nodes than the one that's being constructed here. Okay, let me now step back and talk a little bit about some other applications of these ideas. So here's the context where we have x and y, and now we have L as a confounder, but luckily for us, it's observed. Okay. I now construct the Swig, split on x, get this graph over here. We can apply deseparation. We can read directly off this graph that x is deseparated from y of x given L. There's one path between x and y of x, and L here is a non-collider on that path, so it blocks the pathway from x to y of x. Okay, and it will then follow, this is conditional ignorability, going back into the potential outcome language. It then follows that the intervention distribution, the distribution over y intervening on x, can be obtained via this formula, which is epidemiologists and biostatisticians will just recognize as sort of standardization, where we or in the computer science and causal literature, this is called the backdoor formula. Okay? And we can sort of see that follows by just laws of probability say that this is equal to this by law of total probability. And then by independence, from this independence, I can condition on x. So I can condition on x equals x tilde here. And then by consistency, this is then just equal to the distribution of y equals y, condition on L equals L, and x equals x tilde. So that was confounding. So now let me just quickly show you an instance with a sequentially randomized experiment. So in some sense, this is the problem that Jamie considered back in 1986 without the benefit of any graphs, where we have sort of patients come in, they're randomly assigned to a treatment A, then they then respond. We see them, B might be side effects that they have, some kind of time-varying confounder. C is then a second treatment that is being assigned randomly, but randomly conditional on the earlier history. So for example, your probability of receiving the second treatment C might depend on how severe your symptoms were, how severe the side effects B were that you suffered. And then D is the final outcome that's observed, and D might be the thing that you were originally given A for. And so the kind of situation you worry about is the one where this edge is not present, and sort of patients come in, and A is totally ineffective, but it does make people suffer these nasty side effects, and the people that suffer nasty side effects then get some good stuff that is both not good, not just for the side effects, but also for the final outcome D. And if you were one of these patients, you might say, couldn't we cut out that whole bit at the beginning where you gave me the totally useless stuff that made me have side effects that then led to me getting an increased probability of getting the good stuff? Right? So what we'd like to know is the experiment where both A and C were completely randomized, so where we didn't have these edges from B and A into C. The sort of general result of Rubin says that we can use basically an extension of that standardization formula, a slight extension of it, if these independencies hold. So if A is independent of the final potential outcome, and C of A, this is the treatment that you would receive if you were assigned to A equals A tilde, is independent of D of A tilde C tilde, conditional on your observed history up to that point. Then you could get it by this formula known as the G computation formula, or sometimes the G computation algorithm formula, I think. So the question is, do these independences hold? Well, we just construct the Swig, and we can read them off. Okay, here's A, no pathways to D of A tilde C tilde, so we obviously get that one. Then is C of A tilde independent of this, conditional on this, and A? Well, all the pathways from here, they either go through this node or they go through this node. Right, so I could go like this, or I could go like this, or I could go like this. But our rule for D-separation says conditional on the things we're conditioning on, and also remember we're always conditioning on the fixed nodes. So therefore we get this D-separation. So this general result of Robin's then says that we can immediately apply this, this formula. So this is an instance. One of the purposes of this framework is to provide a kind of Rosetta Stone so that people can now understand qualitatively the circumstances under which these complicated, or somewhat complicated counterfactual independencies would hold. They could write down the graph, and then they could read these off directly by constructing a graph in this way. So just to contrast that, this is the way that Pearl's multi-network approach would go. You would have to make 3 copies of the graph. You'd have to link them together via the error terms. You'd then either have to run the pre-processing step or worry about the deterministic relationships that hold amongst the variables. You know, as you can see, this is a little bit easier to write down than this. But I should add, we are still using Pearl's D-separation criterion on this graph. So our work is building on Pearl's work in a very important and fundamental way. Okay, so some of you may have heard of Pearl's do calculus, sort of introduced in a Biometrica paper in 1995. So the independence assumptions counterfactual independence assumptions that we're building into the Swig are sufficient to get all the results that you would get out of the do calculus. So whenever something is identified in Pearl's do calculus framework, it will be identified under the Swig framework. Let me just quickly say, I've got about 3 slides left. I want to say a word about dynamic regimes. So this case that we looked at here, you might think this was dynamic, but what we were trying to get to was basically we were trying to work out, we did this experiment where the second treatment was assigned randomly conditional on your observed history up to that point in time, but we wanted to work out what we wanted to identify the distribution that we would have seen had treatment being completely randomized at time A and time C. So instead of it being assigned here, conditional on the prior history, supposing we just flipped coins at both points in time. That's of interest, but something that we might be more interested in doing is, say, considering a circumstance where treatment at points in time is a function of your earlier history. So say we might consider different regimes, they could even be random, but different regimes where instead of just always giving you a particular value A1 here and a particular value A2 here, instead we've now come up with some scheme. You know, we think that certain histories, patient histories up to that point in time, mean that you'll have a better outcome if we give you one level of A2 versus another level. So, you know, for example, people worry about over-treatment. They worry about circumstances where you know, we're giving people too much treatment. So you can imagine that we have a rule that sort of says, well, if this intermediate suggests that you're actually doing better, then we're going to stop treating you. So the framework extends to that in a fairly simple and natural way. And it even includes something that sort of is of interest currently. People have been interested in treatments where treatment might depend on the natural value that you would have in the absence of a dynamic regime. So this is the kind of thing where the doctor might say to you, you know, I'm going to ask you to do the following regime. Do the amount of exercise that you would typically do, or 20 minutes every day, whichever is more. Okay, so that your level of treatment, if you're lazy and you wouldn't usually do 20 minutes, then you do at least 20 minutes. But if you're kind of, you know, already doing a lot of exercise, we don't want you to do less. We want you to do how much exercise you would typically do. So in that case, your natural value of treatment could determine the value that you get under a particular regime. So yes, so there are rules that allow us to tell when a particular dynamic regime is identified or not. So in this particular case, y of g is identified, but if we were to add an extra edge here, then it would no longer be identified. Okay, so wrapping up, here's the conclusion. I think that the sort of main point here is that we're eliminating what I call a false trichotomy. So previously, the only approach to unifying counterfactuals and graphs was via this twin network method that Pearl had, which involved translating everything into non-parametric structural equation models very significantly with independent errors. Okay? So any counterfactual model, or almost any counterfactual model, can be recast as a structural equation model. But Pearl doesn't just recast it as a structural equation model, he recast it as a non-parametric structural equation model with independent errors, which is a very significant assumption. So basically, up until this point, there's a camp using graphs, there's a camp using counterfactuals, and then Pearl said, well, if you're willing to switch to this non-parametric structural equation model with independent error framework, although he usually didn't stress the independent errors, then you can have both. Okay? And the reaction sort of is somewhat predictable, that there are people that sort of said, well, like Phil David, who said, well, I'm quite happy using graphs, and the extra assumptions that are involved in the non-parametric structural equation models with independent errors seem somewhat strong, so I'll just stick to graphs. Let's get rid of counterfactuals. Then there are other people, many statisticians and biostatisticians, who are quite happily using counterfactuals, and then they looked at the assumptions that are associated with, counterfactual assumptions that were associated with a graph under Pearl's unification, and they said, wow, those assumptions seem pretty strong, and I can't really imagine any design where I could ensure that they would hold. So if it's okay by you, I'll just stick to counterfactuals and not use graphs. Okay? Pearl was basically saying, and I think he had got further with the people that were already using structural equation models, but he said, well, you can use both, but you'll have to make these assumptions. And these extra assumptions are not experimentally testable even in principle, even if we can imagine experiments like the one with the emetic. Even with those, they're not testable. And they're not necessary for most identification results. So there are some extra identifications that Pearl gets. The mediation formula is one. There are some extra identifications results that Pearl gets out of these assumptions that are not experimentally testable. But in general, for most things that people are interested in most of the time, everything that comes out of the do calculus, you don't need to make these extra independence assumptions. So for example, if Jazz is convinced that independent errors are okay, and I'm skeptical about it, for most of the time, we never have to have an argument about this because most of the identification formulas we'll agree on. It's only for some very special, slightly strange counterfactual quantities of interest where it will make any difference. And so even if I was willing to assume that the errors were independent, I just don't need to bother getting into a debate with someone about it for most purposes. So this basically shows we can use graphs and counterfactuals without being forced to take on additional assumptions. So summarizing and giving you a glimpse of some extensions, I think this provides a simple way to unify graphs and counterfactuals. It links the factorizations between the graph before and after we do our splitting. The new graph represents the counterfactual distribution identified from the distribution in the original graph. It provides a language that allows counterfactual and graphical people to communicate fairly simply, I believe. Two extensions that I haven't covered. It provides a way to combine information on the absence of individual and population level direct effects. So sometimes you might know that the individual causal effect is 0. There might be other times where you merely know that the average causal effect is 0. And graphical language, up until this point, you either had to have your graph having missing edges being absence of individual level causal effects or absence of population level causal effects. It's not that hard to extend the Swig approach to allow you to have some missing edges meaning one thing and other missing edges meaning the other. It also allows us, this is another complaint, so sort of complaints that the counterfactualists have sometimes made about graphs. One of them, a very reasonable one, was if all of causation is built on counterfactual outcomes, and these graphs are causal, how come I can't see any counterfactuals on the graph? Okay, we've addressed that. The second criticism that they make is, well, the graphical people typically, especially if they're sort of thinking about graphs as circuits, they're often very willing to think about intervening on every possible variable on the graph. And especially some of the counterfactualists spend a lot of time worrying about whether or not their counterfactual outcomes are well defined, for good reason. Because being in a position where you're doing an applied analysis and you're talking about the potential outcome, and somebody says, well, how is that well defined? What are you talking about? If you can't give some well-defined possible world where you could sort of say how this would be in principle observable, then people are likely to think you're talking about sort of pure metaphysics. And so this was the second criticism of graphs, that the graphical theory assumed everything could be intervened on. We've also taken care of that. That's it.
Thanks, Thomas. That was great. We have some time for questions.
Thank you for good talk. Since you mentioned it earlier, I was wondering if you could go into those extra slides on how the assumptions of x being independent of y equals 0 and 1.
Yes, let me do that. Okay, so basically, it's not in the case of two variables that the distinction really becomes important. But here I'm just going to say a few words about. So this is about independent error terms and what that means in counterfactual terms. So potential outcomes can. We can always, this is a non-parametric structural equation model. We say that y is equal to some function of x plus an error term for y. These are just really identical notations for most purposes. There are some subtleties about situations with simultaneity and feedback, but I'm leaving those aside. Assuming that our graph system is acyclic, these are just two different ways of writing the same thing. But there's sort of two important caveats that non-parametric structural equation models, at least typically, assume that all variables are subject to well-defined interventions, whereas potential outcomes, we don't necessarily assume that. But the second point that I made is that Pearl's approach associates with a DAG, a counterfactual model, where error terms for different variables, in the absence of confounding, so when everything is observed, the error terms are all assumed to be independent. Okay? So Pearl often will say DAGs and potential outcomes are equivalent theories. He'll make this statement. But the point is that that statement is actually talking just about being able to rewrite this. Okay? And when he's making that statement, he's allowing you to have any distribution you want over the error terms. But when he's typically applying the calculus, he's then assuming that the error terms are independent. So sort of another way to say this is the claim that these are equivalent theories is a little bit like me saying to Jazz, your laptop is equivalent to a Turing machine, so it'll be okay if I take your laptop and give you this little tape with a read-write head on it. They are equivalent in a certain sense, but things may be much easier to, do in one framework than in another framework. So to explain where the difference comes, so here if we look at this mediation graph, x, mediator y, we split on x and we split on m, we get that these variables are independent, x, m of x tilde, y of x tilde, m tilde. These are the independences that we're associating with it, right? And so each instantiation, you have to choose the same value of x here and here, okay? Because you only get the independence, you only see these two variables on the same graph with the same value of x in both places. In contrast, Pearl's independent error assumption gets you some extra independences. It gets you, say, this independence. It gets you that this is independent of this and this. And it gets you that this is independent of this and this. So now here we've got x0 in here and x1 in here. Right? So these are variables that in our framework would never show up on the same graph. Okay, and so here's the kind of quantity. These extra independence assumptions actually identify additional things. Okay? So here's an instance of something that they identified. The pure direct effect introduced by Greenland and Robbins, relabeled to the natural direct effect in 2001, is the following counterfactual quantity. basically it looks at the change in y had x been different, but m fixed at the value it would have taken had x not been changed. Okay, that might seem like a bit of a mouthful, because it is a bit of a mouthful, but in some sense it has a legal motivation, and the legal motivation is the following. That this is from a legal judgment that this is Pearl cites this. The central question in any employment discrimination case is whether the employer would have taken the same action had the employee been of a different race, age, sex, religion, national origin, and everything else had been the same. Okay, so the idea is that X is, say, your gender, M are your qualifications, and this is what we actually saw. You had a particular gender, you had these qualifications, and this was the employment decision. And the question is, if your qualifications had been the same as they actually were, but now we changed your gender, would there have been a different employment decision? And if there would have been, then there was discrimination. Okay, so that's what this quantity is here, right? But notice, this would be hard in general. You know, if we wanted to do an experiment in order to sort of observe this quantity, we would have to take all of you, assign you to placebo, run time forwards, observe your value of the mediator, run time backwards, assign you to x1, and then assign you to the value of m that we saw that you had before we run time backwards. Okay, so it would be hard to observe directly. Okay, people like this because it also allows for a non-parametric decomposition of total effect, the ACE, into direct and indirect pieces. Okay, so that you can get that the average causal effect can be decomposed into a pure direct effect and an indirect piece. So Pearl shows that under what he calls no confounding. So what he calls no confounding is this XMY graph, non-parametric structural equation model with independent errors. Okay, so he's making that independent error assumption. He's making a stronger counterfactual independence assumption than the one we're making with the Swig. He shows that under that, he can identify this pure direct effect. So even though there's no experiment that could get you to it, even though it has this weird character, it's identified. It's identified by this formula. So basically, these are just ordinary conditional expectations, and then this is the distribution of m given x0, summed over m. And people also, yes, actually there shouldn't be an m there, that's a typo, ignore that. Another reason why people like the pure direct effect is you get one number out. Okay, so here's the critique of this. So imagine the following simple hypothetical case study. X is treatment, M is an intermediate like blood pressure, Y is the outcome, say chronic heart disease. Observed data on N subjects, all binary. Supposing X was randomized. So it was a cigarette cessation study. So people were randomly assigned to cigarette cessation or not. Now suppose that we get this data. So this is the data from the study where X was randomly assigned, but M wasn't. Okay? Here's our observed distribution. Okay, and now we've got Professor H, and he thinks there's no confounding. Okay, and based on what Pearl means by no confounding, he thinks that means it's okay to put down a non-parametric structural equation model with independent errors. Okay, he has a skeptical postdoc, Dr. L, who's not convinced, who thinks there might have been confounding, and thinks because there might have been confounding, she's not really happy with the mediation formula being blithely applied in this way. So Professor H, who's very well funded, and has lots of connections, goes and does an extra experiment. He does the experiment where he randomly assigns both X and M. Okay? Does both interventions. Okay? So this is now data where both M and X have been, from randomized experiment where both M and X were intervened on. And here in this, this hypothetical setup, I've given you perfect agreement with the observational study. Okay? So distribution of Y given M and X here perfectly agrees with what we saw in this double experiment where we intervene on both X and M. Okay, so Professor H is now completely convinced. He says, look, I've done every possible experiment. We randomly assigned X, we randomly assigned both X and M. Get off my case, I'm going to apply the mediation formula. And in the particular generating process I've got here, the mediation formula will give you 0. Okay? And he concludes there's no direct effect of X on Y. But unfortunately, there was a direct effect of X on Y. Professor H's conclusion was completely wrong here. Dr. L was right. There was a confounder between M and Y. but the confounder had a special structure. The special structure it had was such that conditional on x equals 0, when we condition on x equals 0, this edge disappeared. So that we get y independent of h, conditional on m, and x equals 0. So h is the hidden confounder. So we get, when we condition on x equals 0, this edge disappears. And when we condition on x equals 1, this edge disappears. So what this means is that the independences that hold under the Swig, the ones that we can test by a randomized experiment, all of those independences hold. So if we try to check for confounding, we're not going to find it. But there is still confounding. The confounding is between the potential outcomes that we can't ever directly observe. So basically, going back here, these hold. These hold, and these are the only independences we can check via a randomized experiment. These don't hold. These independences don't hold, and that's why the mediation formula gives you the wrong result. So I'm almost done here. The confounding was undetectable by any intervention on x and or m. Okay, so the way that Dr. L was able to detect this confounding was she came up with a new variable on the pathway between x and m, and by doing that was able to do a more sophisticated intervention that then allowed this confounder to be detected. I've raised this with Pearl, and this is what Pearl said. He said, the onus is on the researcher to be sure there's no confounding. The mere fact that there's no randomized experiment you could possibly do to check that, even in principle, that's not his issue. He says causation should precede intervention. The fact that he's getting additional things that are identified that could not be identified from any randomized experiment, he sees that as a plus. That's a feature, not a bug. Okay? I sort of see things the other way around. I think, if our only interventions are on the variables x and m, then we can't do an experiment to learn the PDE. So let me just see here. Yeah, so basically, the independent error assumption can't be checked by any randomized experiment. And so the key thing is the connection between experimental interventions and potential outcomes that Neyman had, right? The whole point about Neyman's framework was we're not just going to talk about causation as some abstract metaphysical thing. We're going to reduce it down to missing data in this setup of things that could in principle be observed. And that's gone. Right? As soon as we start allowing ourselves to talk about this, that's severed. Okay? And I basically think that Pearl's claim that, well, the onus is on people to be sure there's no confounding, that's too high a burden to put on people in social and medical sciences. If we're talking about a circuit, it's fine. If it's a physical theory, that's fine. But in the social and medical sciences, I think things are complicated, and at least as the default, people should not be assuming, should not be making such strong assumptions. In fact, his thing about the onus reminds me a little bit of sort of somebody making a nice new fancy sports car and not putting any seat belts in, and then somebody says, well, is this car safe to drive? And the person says, yes, it's absolutely safe to drive as long as it's driven in accordance with the driving instructions. Then you open up the instruction manual, on page 1 it says, it is the responsibility of the driver never to get in an accident. That basically is what this reminds you of. Anyway, I'll stop there.
That's great. I think it's time for people. I think Thomas has some time between now and his next appointment. If people have further questions, they can pester him up here. All right, thank you.